Hi everyone, welcome to Foresight's Molecular Machines Group. Very excited to have so many of you here. Really excited today to be joined by Dr. Iqbal Bakti Utama, and really excited also to see so many of our other fellows and just repeat guests in the room. And welcome to everyone who's watching it on YouTube later. And Iqbal today is joining us to discuss molecular functionalization on low-dimensional nanomaterials for photonics quantum technologies. I'm going to share much more about you in the chat just now, but I'm really excited to call you a fellow this year. Very excited to have you finally on board. Really excited for the Q&A. Take all the time that you need, and yeah, I'll be in the chat answering questions. This is where you can collect questions already. Afterwards, we're going to do questions via hand raise as well. So thanks everyone for joining, and Iqbal, the stage is yours. Thanks.
Thank you very much, Alison, and the Foresight team for the opportunity for me to present my work in this platform. And yeah, my name is Iqbal. I'm currently a postdoctoral researcher at Northwestern University, working in the laboratory of Professor Mark Hersom. I am affiliated with the Center for Molecular Quantum Transduction, and I happen to be a fellow of the Foresight Institute in the year 2023 as well. So today I will talk about the following subject, where I modified the title a little bit from the announcement that Alison and Foresight Institute team has circulated, where I make it slightly more specific, where in this work, we try to see how we can take advantage of nanoscale materials, in particular two-dimensional monolayer tungsten diselenide, in combination with chemical functionalization using molecules and mechanical strain in its application to modify and produce single photon emitters, or also called quantum emitters, for quantum information science application. See, I'm trying to go to the next slide. Okay. The material I'm working on is a member of a broader family called two-dimensional van der Waals materials. This type of materials in its bulk form typically has a layered crystal structure. It's layered because the bonds between the atoms that construct this material are primarily directed in the in-plane direction, in the form of covalent or ionic bonds, whereas the interaction between atoms that form the adjacent layers are primarily mediated only by the weak van der Waals interaction. That's why it's called van der Waals materials. And because it's weak, it's possible to cleave these layered crystals into their ultimate thinness limit, which is just a single monoatomic layer materials. For example, in this schematic, I have transition metal dichalcogenides, where the yellow atoms are chalcogens, such as sulfur, selenium, tellurium, and the middle atoms colored in black is transition metal, such as molybdenum, tungsten, niobium, and so on. And a monoatomic layer of this two-dimensional materials are very thin. It's only 0.7 nanometer for the case of tungsten diselenide, or maybe even thinner for the case of a single atomic layer of carbon, which is called graphene, maybe like. So this is a very broad family of materials, and they encompass various types of electronic, optical, mechanical, and chemical behavior. For example, there are those that are highly conducting electronically, such as graphene. There are those that are insulating electrically, such as boron nitride. And there are those that are somewhat in the intermediate, such as the transition metal dichalcogenides, where many of the members of these materials are semiconductor with various size of electronic band gap. And there are various ways one can produce this material and in their monolayer limit. That includes the top-down approach that incorporates some type of exfoliation method, which includes mechanical exfoliation, such as by the use of commercial Scotch tape method in this celebrated experiment popularized by the group in Manchester, where they start with graphite, like what you typically see in pencil lead, then clip them down sequentially until they get really just one atom thick material. And they get Nobel Prize out of these experiments by studying the unique electrical properties of those material. On the other hand, you can also perform bottom-up method that involves synthesis, such as chemical vapor deposition, where you can get scalable and monolayer in a larger scale. This two-dimensional materials is attracting a lot of interest recently from the condensed matter and material physics community because of their strong tunability of their material properties by virtue of their atomic layer thinness. And as such, a subject that is dear to my heart during my PhD and also in the past few years of my research is to develop new ways how we can control and engineer the properties of this two-dimensional material system. To highlight some of the project that I involved in more recently, it includes the use of strong, intense laser pulses to control the energetics of the eigenenergy of excitons in these two-dimensional materials. We can also use dielectric screening from the environment to tune the properties of these two-dimensional materials that were otherwise actually cannot be tuned easily in when they are in bulk form. That includes, for example, if it transfer this monolayer on the substrate, then the substrate's dielectric properties can influence strongly the electronic band gap of the material. In addition, because of their van der Waals nature, so the bonds in the out-of-plane direction of the material are saturated, you then relax the requirement of having a lattice matching and the need for registry of the atoms in the out-of-plane direction, so that you can then introduce some kind of twisting between the different layers. And as a result, you can form a so-called interference fringe that is now called the Moire lattice. And we then develop and implement scanning probe microscopy imaging technique with that image the microwave impedance of the sample, so that we can view this nanoscale Moire fringes in the sample. And so another implication of the formation is this Moire fringes is a strong modification of the electronic properties of the sample, which we can then visualize using various type of synchrotron-based X-ray experiments, as shown here, where this modification of electronic behavior because of this interlayer twist angle can be dramatic, and then you can observe new electronic correlation phenomena from this two-dimensional material system. But the properties that is of interest for the talk today is the thing called single photon emission. Two-dimensional materials are recently observed to be a host for single photon emitters. So what it is, single photon emitters, as the name suggests, is materials that produce single photons only, just exactly one photon at a particular time, as shown schematically in this top row for these green circles denoting one photon, where the x-axis is a function of time. And this behavior is non-classical. It's like quantum mechanical behavior of photons. Whereas in the classical source of light, like for example, your lamp, or even lasers, for example, the type of photon statistics can become somewhat random. So occasionally you will have more than one photons, some other time you have one photons. But in the case of single photon emitters, you exactly have one photon at a time. And the experiment tip that has become the gold standard to verify this photon statistics and whether you really have single photon emitters is the so-called Hanbury-Brown twist setup, as shown over here, where the light is then passed through a 50-50 beam splitter towards two separate detectors, and the light being detected are then correlated in time to form the so-called second order correlation function as a function of time delay being the time that has elapsed after which or before which a photon arrived onto one of the detector. So if you have a single photon emitter, you should expect to have a dip over here at time 0, which means you don't have another photon arriving at the other detector when one photon arrives on one of the detector. And the criterion to say that you have a single photon emitter is when this second order correlation function value at time 0 is less than 0.5, as shown in this image. Single photon emitter has potential application in quantum information science. This includes the use of single photon emitters in quantum computing as a building block to perform integrated quantum network where you can encode information, for example, in the polarization states of these single photons, and likewise taking advantage for the fact that the photon is mobile. It can travel long distance with the speed of light. They are really light. in literal meaning, and they actually don't interact much with the environment. And as a result, you can use this information that's encoded in this single photon for quantum communication over distant nodes. You can also perform various type of other studies, including, for example, quantum sensing using single photons to get high resolution sensing of biomolecules, and also fundamental science studies, for example, using single photons as a probe for light matter interactions at the nanoscale level. And since I'm talking at the forum of Foresight Institute, I'd like to quote what Richard Feynman says in a talk that is memorialized in this paper, where even though there is a lot of hype for quantum computing in the recent years, where it's expected that it may have significant impact in society for performing calculation on problems that is not easily solvable using classical computation using silicon transistor electronics. For example, for modeling financial market or climate change, or maybe simulating large molecules for drugs. And in particular, simulation of large complex molecules and solid state systems is very relevant to the talk that Feynman gave many decades ago, where he recognized that given nature is not classical, it's actually quantum mechanical, and therefore the best way to simulate nature is to make advantage or to take advantage of computational methods that is also quantum mechanical. So this material of interest, monolayer tungsten diselenide, which is member of this two-dimensional van der Waals materials, has been reported in 2015 by a series of papers from different groups as a single photon source. So when you cool down this monolayer tungsten diselenide to a sufficiently low temperature, something like only in the regime of few Kelvin level, you start to see emergence of many sharp lines, where this sharp lines with line width of sub-millieV sharpness shows a dip in this second order correlation function, which indicates they are really single photon emitters. So it is believed that those emitters are originated by point defects within the crystal of the tungsten diselenide that may include selenium vacancy. It shows anti-bunch emission. What it means is basically it shows this dip in the correlation function. And in the earlier demonstration here, the emitter are typically randomly occurring and randomly positioned on the sample, like in this PL map on the sample that looks triangular over tens of micron, bright spots, this red dots over here, they show up just randomly all over the sample without much control. But that was in the earlier years of this topic. But then there are more papers showing up. It's been shown that if you try to couple this monolayer tungsten diselenide with dielectric nanopillar, so if you suspend this monolayer tungsten diselenide on array of dielectric nanopillar, thereby producing localized mechanical strain, you can then induce some kind of hybridization between the dark states of within the tungsten diselenide within and the defect states, activating the emission at the location close to where the strain is maximized. So then you have single photon emitter that is deterministically positioned where the dielectric nanopillar are. So in the AFM, it looks something like this. You can have an array of nanopillars, like as numbered, and then the emission shows up at where the nanopillars are. And then afterwards, modify and improve the behavior of the single photon emitters, typically shortened as SPE, using various type of experimental knobs, including electric field, DC electrostatic gating, electron beam exposure and irradiation, and some kind of Monix near field coupling. But one of parameters and experimental knobs that has not been utilized much in the literature for tungsten diselenide in particular is the use of chemical functionalization. And this is actually unfortunate because of the fact that monolayer tungsten diselenide is very thin. It's just 3 atoms thick. And therefore, given of the all surface nature of this material, you would expect that the surface and interfacial engineering of this material can be very effective in controlling and modifying the behavior of tungsten dazzle as a whole, and also in particular to modify the quantum emission properties arising from this monolayer tungsten dazzle night. So that becomes the question of our research studies in this talk, which is to see how we can use molecule and molecular functionalization to modify the single photon emitter behavior in monolayer tungsten dazzle night. And the way we go about it is to use an approach we term chemomechanical, where we try to combine synergistically the effect of mechanical strain induced by suspending the monolayer tungsten dazzle onto this dielectric nanopillar, and functionalize this monolayer with the use of molecules like shown schematically in this image. So the chemistry that we implement in this study is the use of nitrobenzene diazonium in aqueous solution, where it is believed in the literature, if you dip a material into a solution that contains this nitrobenzene diazonium ions, you would then withdraw electrons from the surface of the sample being tungsten diselenide in this case, because of the strong electrophilic nature of the diazonium ion. And this electron is then, let's see, is then used to break these nitrogen triple bonds over here to create aryl radicals. And since radicals are very reactive, these radicals are expected to bind covalently to the surface of the sample, forming nitrophenol, or in short, NPH. And since it's also so reactive, they can also bond to each other to form the so-called oligomers shown here. And there are many studies that follow this scheme. And in addition, diazonium functionalization, because of its strong electron withdrawing nature, it has been demonstrated as a very efficient hole doping scheme, where you can see p-type behavior from field effect transistor out of a tungsten diselenide device that is exposed to this diazonium solution. So this is how the sample behave optically in our experiments. If we place tungsten diselenide on a substrate, cover 1/2 of them with an insulating boron nitride flake, we see that the part of the sample that doesn't have the boron nitride cover and thereby exposed to the diazonium ion experience a significant photoluminescent quenching in terms of its intensity from before, which is this blue curve, it becomes the red curve over here. So there is a strong drop of the photoluminescence intensity. You can also see that effect in this PL mapping of the intensity, where the part that doesn't have the boron nitride cover becomes dark. But in addition, we also see a red shifting of the PL peak position at the part that is exposed, and also broadening of the photoluminescence line width. That was the case for the room temperature. How about at low temperature, at temperatures of 1.7 Kelvin? So at the region of the flake that is flat, so this is atomic force microscopy image, the flat region shown in this orange square, originally it looks like this blue curve. You have a lot of peaks that can be assigned to normal excitonic complexes, including nitro exciton, bi-exciton, trion, and dark exciton. But then after you expose them to the diazonium solution, the PL intensity is quenched. It becomes this red curve. You don't see those fine structures anymore. The intensity becomes weaker. So it's in general in alignment to what you see at room temperature. But then something interesting is observed at the region where you have strain, as shown in this green circle, where you have wrinkle on the substrate. So there is localized strain because of the wrinkle. Originally, you have many sharp peaks that are bunched together, which is this blue curve, and that sharp peaks comes because the defect states becomes radiatively active. You can start to see radiative recombination coming up from the sample because of strain. But then after functionalization, and in addition to quenching of many of these defect lines, peaks showing up that are well isolated energetically from each other. This sharp peaks is very nice because even though many of those peaks before functionalization may be single photon emitters to begin with, but they are too closely spaced to each other, and thereby preventing further characterization and isolation of the single photons from the sample. But then once they become well isolated like this, you can then perform a collection of the single photon and characterization sample, including the so-called Hanbury-Brown twist experiment to get the photon statistics I mentioned earlier. This is further characterizations we can do after functionalization on those sharp peaks. It has the typical behavior of single photon, like in tungsten selenide as usual. It has sharp sub-millieV zero photon line width. It shows saturation of the PL intensity with excitation power. And more importantly, we also see this dip in the second order correlation function with G value at time zero that very close to 0.01 after background correction. So indeed, that sharp isolated emission feature after functionalization is really single photon emitters. And also we can perform anistic positioning of this chemomechanically modified single photon emitters using the scheme that employs directed nanopillar array, where we transfer the monolayer tungsten diselenide using our setup, which is basically micromanipulator under optical microscope. So then we can perform deterministic positioning and transfer of just this 3 atomic layer material onto this arrays of nanopillar, and then perform functionalization on the surface. So we have this mixed dimensional heterostructure of the 2-dimensional monolayer tungsten diselenide, this quasi 1D structure of nanopillar array, and then the 0-dimensional of nitrophenols. And as before, we see simplification of low temperature emission spectrum, where originally you may have many emission lines, like in this blue curve, but then after functionalization, it becomes the red curves where there are sharp peaks that are just energetically isolated from each other. And then you can perform this second order correlation measurement and show that it has a dip at time zero. So we then also perform more characterizations on the sample to try to understand the nature of the interaction between the nitrophenol film that forms after the functionalization with diazonium, where our experiment suggests that the whole doping effect, because of this electron withdrawing step, is not the only or primary mechanism that causes the PL quenching. And also the nitrophenol film that forms is mostly physisorb. It doesn't form covalent bonds like what is typically believed in the literature. So I'll go through step by step the 3 experiments we do to make this conclusion. So in the first experiment, we perform scratching of the nitrophenol oligomer film using atomic force microscope in contact mode. So it's schematically illustrated in this diagram, where originally this tungsten diselenide have a nitrophenol oligomer coating on the surface. Then we use the cantilever tip of the AFM, use it in contact mode, apply some normal force, and then drag it out laterally over the surface. As a result, although originally the sample has oligomer coating everywhere, like shown here in this AFM image, after the AFM scratching, we can open up a window like this square window. So the scale bar is 2 microns, so it's 2 times 2 micrometer square window where you no longer have oligomer coating on the monolayer tungsten diselenide. And then a line cut over here in this red curve, you can see the profile over here. You get the thickness of about 4.4 nanometer from the oligomer film. That indicates first, the oligomer interaction with the monolayer tungsten diselenide is relatively weak. So if you have a covalent bond, typically you would expect much stronger interaction, and removal of the nitrophenol would typically damage the tungsten diselenide itself, but that is not what we see. So that is more consistent or typical from what you would expect of a physisorb film. But more interestingly, also, if we perform PL mapping of this AFM scratch sample, we see that the region where the nitrophenol oligomer film is removed in this square window recover their PL intensity. So in this PL intensity map, the part that doesn't have nitrophenol oligomer becomes bright again. So the quenching effect from diazonium treatment is actually reversible. And moreover, we also see reversion of the peak position. It becomes blue shift again, and then the peak width becomes sharper again, as also shown in this PL spectrum extracted from the region with AFM scratching, which is black curve, and then red, which is obtained from the part that still have nitrophenol coating. So the conclusion from this experiment is that the direct and continuous contact of the nitrophenol oligomer to the monolayer tungsten diselenide is required for getting the PL quenching. In addition, we also perform another experiment, which is to do dry transfer of the nitrophenyl oligomer film that is assisted using boron nitride as a scaffold for the transfer. And doing this dry transfer then circumvents the need to do solution phase to expose the monolayer tungsten diselenide to do the functionalization. With dry transfer, with the help of boron nitride, like shown in this schematic, we circumvent the need for this step, which is the electron withdrawal of electron by the diazonium ion in the solution phase. We no longer have this step. So instead, we start directly with the nitrophenyl oligomer that's already on HBN transferred in a dry environment to the tungsten diselenide. So therefore, with this experiment, you don't expect to have a whole doping effect anymore. So the way we go about it is so we first exfoliate tungsten diselenide monolayer on silicon substrate. It is dielectric, and then we cover one half of the sample with inert boron nitride flake, like so. And in parallel, we prepare a boron nitride flake on a PDMS polymer. And this sample is what we dip into the solution that contains the diazonium ion. So then this boron nitride is now coated with the nitrophenyl oligomer. And then we transfer this boron nitride with the nitrophenyl with it to the surface of the tungsten diselenide that remains exposed. It doesn't have the boron nitride. This is how it looks like at the end. And we can then perform PL mapping on this sample. Whereas originally the PL map of the sample without any nitrophenyl and before any HBN transfer looks uniform everywhere, but the part of the sample, the monolayer tungsten diselenide that is in contact with the nitrophenyl oligomer that is dry transferred becomes quenched. So in conclusion, you can have this PL quenching effect even when you don't have whole doping and even when you don't have covalent bonds between the nitrophenyl and the tungsten diselenide, because we do this in a dry transfer manner. And also, last piece of experiment that we perform is through the use of X-ray photoelectron spectroscopy, where we compare the spectrum of the tungsten and selenium core levels before and after the treatment with diazonium ion. In both the tungsten and selenium core levels, what after the diazonium functionalization is that there is some chemical shift towards the lower binding energy. So you see the curve shifted to the right for both cases after functionalization, which is in the lower rows. And this in the literature has been observed and was ascribed to a whole doping effect, because this in this particular case is functionalized in solution phase. But more importantly, in this experiment, we don't see any change in line shift for both the tungsten and selenium core levels. So the spectrum looks identical before and after functionalization. There is no emergence of new features in both cases. And in fact, if you superimpose these two curves together, like in this case, it looks identical. Before, which is the black curve, and red, before, which is the red curve, and after functionalization, which is the black curve, they actually overlap with each other almost perfectly. So this suggests to us that the nitrophenyl functionalization that sits on the surface is really physical rather than covalently bonded on tungsten diselenide. So with the help of our theoretical collaborators, Dr. Tumpas Adhukan in the group of Professor George Schatz, and I should note that Professor Schatz is a recipient of the Feynman Theoretical Prize from the Foresight Institute some years ago. They help us to do first principle calculations of the band structure of this nitrophenyl and tungsten diselenide heterojunction. So in the original case of the strain tungsten diselenide with 1% strain, with the selenium monovacancy, we have this defects because this is what is typically attributed as the origin of the single photon emitters. You would have originally dispersive bands colored in purple, so that comes from the intrinsic tungsten diselenide itself. So this is the VBM, this is the CBM, connection band and valence band maxima. And then if we have selenium vacancy, then we have this flat bands colored in green, close to the valence connection band edge. But then after we incorporate nitrophenyl oligomer, like in this particular case, we have the 3-ring configuration of the nitrophenyl. We start to see new flat bands as shown in red, close to the connection band edge and almost matching the position of where the selenium vacancy is. The fact that it's somewhat lower than the conduction band minima of the tungsten diselenite indicates that we could have a type 2 heterojunction formation. And this is consistent to our observation of PL quenching of the tungsten diselenite PL at room temperature and also low temperature. And also, although it's not shown here, but what the theoretical calculator have calculated is that because of the fact that the nitrophenol can form in other type of configurations beyond these 3 rings, it can also form other types like 4 rings, 5 rings, and even more length of chains of the oligomers. You may thereby have a polydispersity of the nitrophenol oligomer configuration, and you may have different alignment of how these flat bands from the oligomer metals actually position with respect to the selenium vacancy bands and the conduction band edge. So at some cases, you would expect it may have position lower or overlapping with where the selenium vacancy is. So that is schematically drawn over here. And what we expect to be the mechanism of how the quenching occurs, and the one that gives us the simplification of the spectrum, is that for a certain type of oligomer state configuration, you have this mid-gap states from the oligomer orbitals, and they are positioned lower or in resonance to the selenium vacancy and defect states from tungsten diselenite, and therefore you can get charge transfer or energy transfer that then quench the emission that comes from these states. So instead, the excitons, the trapped exciton, will try to find the lower energy states available and then recombines only from there. So you will have fewer emission lines because much of the defect state that are originally available now becomes inactive anymore because of the presence of the oligomer states. So then, in conclusion, we have demonstrated a new pathway to modify the single photon emitter behavior in two-dimensional materials using molecular functionalization, which is an unexplored parameter space. And given there are so many chemistry you can employ and so many different type of molecules and two-dimensional material combinations, there are so much room to explore to see how we can get a nice or more interesting single photon emitter behavior with these combinations. Or what Feynman once says, there is plenty of room at the bottom. As a second point, specific to the experiment that we performed using diazonium treatment for the case of strain tungsten diselenite removes much of the parasitic defect emissions, where originally you started out with so many emission lines, but then after functionalization, you get emission features and peaks that are well isolated energetically. Then you can perform a more detailed single photon emitter characterization and obtain single photon emitter with high photon purity. And then with the help of our theory collaborators, we show that the quenching mechanisms involve a type 2 heterojunction that forms between this zero-dimensional nitrophenol and the two-dimensional monolayer tungsten diselenite. And as a vision on what can be done next, and what we are also currently trying to investigate, we have written up a review article recently published in Material Research Society Bulletin, where there are 3 different directions that we believe is worth exploring in this mixed dimensional heterojunction formation. One of them includes the exploration of different combination of the functionalization scheme and chemistry to modify the single photon emitter into dimensional materials. And in fact, one potential direction that has been predicted before but have not been seen experimentally is to see whether we can actually generate the single photon emitter in two-dimensional materials after covalent functionalization without the need for employing any kind of mechanical strain on the sample. So the single photon emitters directly comes from the interaction of molecule and two-dimensional materials. It's also interesting to see how the single photon emitter can be used in application. For example, how we can use the properties or behavior of the single photon emitter as a proxy to study the electronic state of the host materials. Like in this particular diagram, this is actually a measurement from Srivastava group, where they use the single photon emitter related electronic state within the two-dimensional materials and heterostructure that host these emitters. And lastly, although much of the studies used in two-dimensional materials involve mechanical exfoliation that has very low yield and throughput, it's also interesting to see whether this kind of material system can be made in more scalable manner. That involves, for example, the use of bottom-up chemical vapor deposition synthesis, like shown in this schematic drawn by Aronovich group. But you can also envision other types of sample preparation or material preparation technique, including, let's say, additive manufacturing approach that involves the use of solution exfoliated materials that is using various types of printing techniques. Okay, and the final slide here, I would like to acknowledge all the collaborators and people who I work with, including my advisor Mark Hersam, Anushka, that works with me a lot in the chemistry and sample preparation, and our collaborators in the spectroscopy STEM group, Hong Fei Zheng, and our theory collaborators George Schatz and Tumpa Sadukan. So thank you very much for your attention.
Wonderful. Thank you so much. That was fantastic. That's quite the really nice walkthrough. Thank you so much for that. I don't know if anyone wants to start with a question or so. You already are receiving like a few virtual clap hands, which is always really nice. Maybe I'll wait a minute or so. Otherwise, I'm going to ask you my standard Foresight questions. Oh, Caleb raised his hand. You go first, and then we'll go down the line.
Great talk. Very interesting stuff. I had a couple questions. One is the dry transfer process with the PDMS. Can that be done reversibly? Can you, using maybe a different material, actually remove a oligomer from selected regions of the surface?
Yeah, so an experiment that has been done, although not in the same experiment as when we did the dry transfer, we actually used this AFM scratching technique. Yeah, so by using AFM in contact mode, you can scrap away the oligomer coating and then you can reverse the photoluminescence behavior of the sample. But back to your original question, I would expect the answer would be yes. So nitrophenyl oligomer may stick better to the boron nitrate layer. So then if we have a polymer layer that is sticky to the boron nitrate, you can imagine you can pick up the boron nitrate and the nitrophenyl oligomer along with it. And then you would end up with the same result.
Yeah. Okay, so different ways to pattern. I guess the other general question I had was in terms of different oligomer chemistries or functionalization directions, where are you most interested in going next?
So one of the experiments that we have currently ongoing is to see whether there are molecular functionalization that behaves in somewhat different manner than this the one produced by this diazonium functionalization scheme. For example, there are molecules, conjugated molecules that has more monodisperse than the diazonium oligomers, nitrophenyl oligomers. And as a result, you may have more well-defined orbital states within the mid-gap of tungsten diselenite. This may include, for example, you can imagine depositing tetracene, pentacene, or some other related molecules that therefore you can also employ other type of fabrication methods. Whereas this diazonium functionalization, we have to use solution phase. With those other type of molecules, you can employ, for example, sublimation technique in vacuum. And therefore, you can open up other new ways to pattern them using shadow masks, for example. And also, the different type of molecules for sure will result with very different energetic alignment of the orbitals. So something that we are interested to see is whether rather than type 1 heterojunction, type 2 heterojunction, if we get a type 1 heterojunction with the orbital gap of the molecule being larger than the tungsten diselenite band gap, you then would expect to have enhancement of this SPE emission intensity rather than quenching that we see in our work with nitrophenyl and diazonium treatment.
Are you all good, or is there a follow-up question you want to ask, Caleb? Yep.
Oh.
Then maybe I guess my follow-up question is like along the lines of Caleb's, but perhaps like a little bit thinking almost a little bit further out. I know that people don't often like to speculate, but it would be, I think, really interesting to just consider on the next, 5 to 10 years or something. Where do you see this technology going, and do you see any potential like applications along the line that could be really useful for folks on the longer term time scales?
I see. Yeah, so one of the unique advantage of photonic quantum information science is really the fact that photon can travel over a long distance. So something that has been demonstrated maybe 2-3 years ago by a group in USTC in China, they actually use entangled photons to perform communication or transfer of this quantum state over distance like hundreds of kilometers away. So they actually specifically try to launch a satellite into outer space where they have their experimental instrumentation to perform this quantum communication over distant nodes. So that's actually one of the key advantage or key prospect application that is unique to this photonic quantum information science infrastructure. But specific to monolayer tungsten diselenide material system, I do foresee that there are a lot of rooms for it to improve to get to the level where it can be suitable for practical applications. Like one of the main thing that people in the quantum physics community will question is about coherence time. So the coherence time of single photon emitters in tungsten diselenide is relatively short, something on the nanosecond time scale. There are other kind of qubits that have much more promising time scale of their quantum coherence. One example may include some kind of point defects inclusion or substitutions in silicon. I remember Professor Michelle Simmons in Australia, who is actually one of the speakers in Foresight Institute, reported about this qubit infrastructure. It has microsecond lifetime, like 1,000,000 times better than single photons. But then it's like spin qubits, it's not mobile, unlike the case of single photon emitters where the photon can travel.
Okay, awesome. Yeah, I just shared Michelle's recent seminar with people here in the chat for those that want to check it out. Actually, it was off the record, but I think there's like a hidden YouTube link that you guys can find. Yeah, wonderful. Thank you so much. That's really useful to know. I think one other thing that oftentimes people are really curious about, especially if they're just newly entering the field, and I think you touched on a few bits and pieces of that, but it could be cool to just spell it out once more, is in terms of like specific challenges that you think this type of work will be facing in the near-term future. Let's say, imagine there's a new researcher entering the field right now, and they're wondering how they could plug in. Do you have any bits and pieces to point them to where you're like, oh God, if someone would just solve this challenge, then everything would be so much easier? That would be really useful to know.
That is a broad questions that indeed difficult to answer more specifically. But as you have known, quantum computing, quantum information science is a space where there are a lot of players, even industry and academia, that are really actively trying to invest and investigate a lot of efforts into developing architecture of the quantum computing that actually works. And there are very different materials. Can you still hear me?
Yeah, you were cutting off a tiny little bit, but now
Oh, wait, okay, so you can still, okay, good. I was getting a pop-up window saying problem with my audio, but okay. Yeah, for example, a startup that try to employ superconducting base qubits. There are those based in Massachusetts that try to use cold atoms, and there are also those that use trapped ions. There are like us who try to use nanoscale materials and study their emitter behavior, like photons as the qubits. There are those, as mentioned in China, that also use photonic quantum information science. There are those like Michelle Simmons that use spin qubits in solid state systems. So all those different architecture have their own problems and issues that they are trying to solve. Specific to our architecture, I mentioned about coherence time that is still very limited. There are issues about, for example, uniformity and how we can make the properties of the photons to be much more controllable and deterministic. So I mentioned one of the topic about control, which is positioning, but there are also other aspects. For example, how we can control the emission wavelengths to be much more uniform between pillars to pillars. So in our experiments, we typically see a spread of wavelengths that is not good. So we want to make the range to be much more narrow. Likewise, the line width for the emission of the emitter is still rather broad, is still in the milli-eV range. We want it to be much more narrow. There are other type of solid state emitters where it can have gigahertz line width, for example, and therefore it means you can have better photon indistinguishability, and you can get more coherence between the emitted photons, and you can get this nicer quantum mechanical behavior among the qubits. But in general, any of those experiments require very dedicated and specialized instrumentation. Like I mentioned, much of the experiments that we use require very low temperature, like 1.7 Kelvin. Some other experiments on architecture requires even more extreme conditions, like millikelvin, 1,000th the temperature that we use in our experiments. That is typically the case for superconducting qubits. And therefore, you wouldn't expect to have quantum computing in your consumer electronics, like in your pocket yet, as of the next few years, for example.
Wonderful. I actually had a few friends who worked at Rigetti.
Oh, very nice.
It's coming up in this setting. Okay, really cool. Then perhaps like another one that could also be interesting is, does this work have any implications for like more long-term goals of molecular manufacturing, or like molecular 3D printing, or autonomy precise manufacturing, like the old school Foresight goals? Do you see any like, potential kind of like bits and pieces where that could fit in? And it's totally fine if the answer is no, but I think it's usually like an interesting question if there's like a part of the toolbox for that could be built with this stuff.
Yeah, of course, in some of the experiments we performed in this project, we have actually tried to incorporate some of the ideas that was in parallel also discussed in this manufacturing, this molecular machine manufacturing. For example, I was mentioning about using scanning probe microscopy, using this sharp cantilever tip to control where you don't want the molecule to be. Like in the case of molecular machine fabrication or manufacturing, you put molecules in using the cantilever, but instead we actually remove the molecules using the cantilever. But of course, let's say one of the direction I was mentioning in the next step experiment, which is to see whether we can generate the single photon emitters with the molecular functionalization that forms covalent bonds. Imagine if we can very controllably position just a single molecule in a specific position on the monolar tungsten net with the exquisite control of the position down to the molecular level that then creates chemical bond on the surface. You can imagine you have more uniform or a higher precision of control of for example, first the energy, because then you will have more control over the exact configuration on how the molecule is sitting on the surface. And secondly, in terms of positioning, obviously, because then if you have atomically precise manner in which you can control where the molecule is sitting, you can have the single photon emitters to start to show up with maybe, let's say, nanometer scale precision on the sample, as opposed to hundreds of nanometer scale precision like what we have with the use of dielectric nanopillar positioning. Yeah, that would be it.
That's a wonderful answer, and especially because it was off the cuff. So thanks a lot for taking that one. That's definitely like a more challenging, I think, thing to still piece together in your mind. Okay, maybe final question for me is, if people are excited about your work, how could they help support you? Like, what is your lab up to, like in the next few months or so? What's your group working on, and what are you in particular working on? And are you looking for specific collaborators, like in specific fields, or are you looking to explore perhaps other fields, or like making a career switch? Whatever it may be, it would be really wonderful to hear if people are excited about your work and like about your direction, how they can help you as a person.
First of all, I would mention that I will, at least as of now, attend the molecular machine workshop next week. If people in the audience is also there, we can discuss in more details about my project or how the kind of experiments that I described can be helpful for your experiments or projects. So in more specifically toward Alison's question, we are still in deep dive towards developing this architecture of the use of a combination of molecular functionalization on nanoscale materials in creating or modifying the photonic qubits. That I foresee to be the kind of work that I and our lab will continue to do over the next 2-3 years, as long as the grant funding persists. And me on the personal level, since I am in a postdoc position, within the next 2 years, I will try to look for faculty positions at research-intensive universities. So I'm in the lookout for job opening and therefore potential funding opportunities that may be interested on this kind of the direction or space.
Great. On that note, I think it's also perhaps like a good segue into first thanking you also very much for joining and really excited for the upcoming workshop here. So this is our upcoming workshop that we had already mentioned. And this will be, next week already. Damn. By today, next week, we'll be through with this. But we'll be discussing mostly like long-term goals towards molecular 3D printing and how we can build architectures for that. And I'm really excited to have so many of you joining this workshop. And for those of you on YouTube who are wondering, it's accessible via our website. It's unfortunately entirely oversubscribed for this year, but we do have them every year. And so we're excited to see so many of you there. And with that being said, thank you so much, Iqbal. It was such a pleasure to have you on. Really excited to see many of you in person in a few days. And very excited to see you afterwards for the seminars again. So thanks, everyone. Hope you have a wonderful rest of your day.